Yeah, I think a group had already met for this paper last week.
Yeah, that I think.
And then they posted the notes that they got, and then that's all the time.
Yeah, I was part of that little meeting. It was like last Thursday.
Oh, okay. So I just took the information from there and incorporated it.
Where's that on the Slack? It's just somewhere.
It's just on the whatever paper one this is. So then just go on that channel.
Are you guys in paper channels? If you
How do I get in?
okay.
Sorry.
No, you're good. I didn't know this either. I had to ask.
Yeah.
If you go to like the channels at the bottom, you can click Add Channel, and then Browse Channels, and then it'll show you all the papers.
Yeah. Did
And
you not
that's-
know that,
No,
Rebecca?
No, it didn't.
You showed me actually, right? You
I
showed
didn't
me.
say
That's not good.
Wow, that's so cool.
Yeah.
Not
So
that
even
a lot's been mentioned. It's mainly people being like, "When are we meeting?" But a couple papers they have like posted notes, but they weren't like very extensive notes. Or maybe they, I don't know. But yeah, that's how you find the papers. Which also I looked in paper 12 and saw that there was nothing from Bonnie, so that's why I was like super confused.
Oh my gosh.
But which is also where I got
So
this
we're-
XRD paper. Actually, maybe that could have not been in a channel paper. I don't remember. Anyway, yeah. So okay. So for the sake of this video, this was Bragg's law. Over here is like me deriving Bragg's law.
There is something in paper 12.
Oh really?
Yeah.
By the
Since
way-
we want to discuss this tomorrow afternoon, yesterday.
Okay. Well, my
other than mine, what are the ones that are being done today? Here.
12. Wait. In this meeting?
Yes.
I don't know. Whatever anyone else wants to do.
Oh, okay.
I mean, I have another presentation I can do as well, but if you want to do one too.
Okay, yeah, no, I had mine that I needed to do.
Okay. All right. I'll keep going. How to read diffraction patterns. Okay. You get 2 theta values from XRD, and then from there you calculate D-spacing and relative intensity. I don't know if this is like an industry thing. I think it is, and it doesn't really get discussed in this paper specifically, but I think with XRD is you have to normalize all your intensities. So you find your highest peak. So here, one of these is highest peak or something. Oh, here. You set that equal to 100, and then you would calculate everything else based off that. That's, normalization. I think this is the high, one of these is, I don't remember. One of these is like the highest peak,
Oh.
or highest intensity. Set that equal to 100, all that. And then you use the D-spacing information from the 3 most intense peaks to match on the Hannawalt manual, which is card numbers. So they mention the card numbers throughout here. I don't think it's like relevant for the like understanding of the paper. It's just them being like, we were able to confirm that this was grown or this was created using the card numbers. So I thought this was a helpful reference. There's a whole manual with a bunch of card numbers for different materials. And this is for multi-phase. You do this just for one phase. So you're assuming one phase has a higher concentration. You compare the measured XRD to the PDF. It's called a PDF card. You subtract out the PDF pattern from the first phase from your experimental data, and then you do this all over for the second phase. I don't know if this is exactly what they did, but this is what we were vaguely taught in class. Yeah. I love how this slide is blank. I don't know what else I wanted. I think I wanted to put more information here and I didn't. Higher the intensity of the peak, larger concentration of that family of plants. I think I was gonna go back and put in more XRD information from class, but I don't know. Okay, now they talk about integral breadth method, which is a bunch of stuff that we also learned kind of in scattering, which is called full width half maximum, is basically like
They mentioned this in the 2D paper too, right?
Yes, it's a very common way. Which is like the distance from like here to here of the peak of whatever like half the maximum is. I think that's pretty self-explanatory. And then this is the equation that they use. They talk about like Lorentz and Gaussian distributions, which I'm sure we've seen before. Then they mentioned Cauchy and Gaussian distributions. Apparently this is like what I found online of like Cauchy versus Gaussian. And then if you, what do they call it? Transpose or like transcribe the two together, you get a Voigt function, which is, I think, I didn't draw it here, but it's like slightly smaller.
Is that a linear combination?
I
I want to say it's linear.
Cauchy component. Wait, hang on.
I feel like it's like
Deconvoluted.
Okay.
So it's deconvolution. Didn't touch on that because I don't really know what it is.
Integral math complicated.
Yeah, it's like all
Don't
math
bother.
based, whatever. They also mention.
Is it when the peaks are kind of like all shouldered and stuff, and you like delineate them? Is that
I
what
think
the
so.
deconvolution
Like
is?
rolling past each other, kind of.
Yeah.
Just integrate.
I didn't think it was relevant because they just used the two functions to create what is considered a void function,
Just
and
think
then
of smashing it together.
yeah, which they use which I can talk about. They use the Cauchy component of the void function is for crystallite size, which is this equation, and then the Gaussian component of the void function is for strain, which is this equation. Then they mentioned that they what did they say here? The size strain analysis in terms of integral breadths is simple enough and can be performed using the Scherer equation, which is this. They don't mention the equation. Must be like a very known thing. But this is a pretty like common equation that people use in like XRD analysis and crap. Then they do multi-line analysis, and then they talk about Williamson-Hall plots, which we definitely did in scattering, which I definitely forgot we did until we looked at the notes. Which is basically like a size and strain analysis from your XRD. Yeah. And then they go into Fourier transforms. They talk about specifically this Warren and Averbach, whatever method, which there's like a whole page on this bullshit, but this is it summarized because it didn't really feel important, other than like the measured X-ray diffraction lines can be expressed as a Fourier series, which is this. Then they talk about what the different terms mean, specifically that L takes discrete values n times delta L, where delta L is the inversely proportional to the length of the measurement range. And then that can be expressed as order independent size and order independent, which is like size, like crystallite size, and order dependent strain coefficients, which is this like ASL and ADLS. Yeah, you need two orders of reflection to understand these coefficients. So these are, I mainly like include this because that's clearly what we're looking at is crystallite size and strain. So yeah. And then they do this main thing, Warren Averbach, I think is all done computationally for the most part. And it's basically they're like fitting a known, they're fitting known components to your calculated data, and they just keep like refitting it until something matches. Yeah. Profile shaped function fitted to a measured diffraction line. And okay, go away. Line intensity, peak intensity, and I think full width half maximum is what this says here. I want this to be so bad. Yeah, so those are the points that's basically what they're looking at from the XRD pattern. Oh, there we go. Line width expresses full width half maximum. Those are the three things that they're looking at from the XRD patterns to be able to like answer the question in the paper. Okay, so now we're getting into this experimental part where they're doing the synthesis of alumina templates. So they're making alumina templates and then the alumina zirconia nanocomposites. So they're using undoped tetragonal cubic phase zirconia, can be stabilized at room temperature by controlling the crystallite size. So they need to be able to prepare templates with pores that are less than 100 nanometers. So they're using this alpha aluminum 2 trioxide, I don't know if that's how you say it, with limited solubility in zirconia. So basically they're like trying to use a substrate, or a template, because they're like growing the zirconia within the aluminum. They're trying to find something that will not deter the environment of growing the zirconia.
So it's like they want, because I remember them casting, they're like making the alumina template with the zirconia in it, and then they would like let it bubble up and stuff, right? So you're saying that, I think the main point with that, it doesn't, what was it again? Yeah, there's no solubility, is that you don't have stuff in the bulk of the alumina, I think.
Yeah, so the zirconia like won't morph into the alumina. Like you can be able to see discreetly like what is the template and what is your zirconia that you're growing. I don't know why that I with the two things is there. I think I meant to say it. Literally don't know how that came about. I think it gives info on oxygen vacancies, if any, they say. That's the thing too. Again, they're like, give info on oxygen vacancies, if any. But like the main question they're asking is about oxygen vacancies. So that was something that I was a little bit confused about. They use solution combustion synthesis, which they don't go into a ton. I kind of looked into it, but maybe I wasn't like too deep in it. Where like a large volume of gas occurs, the particles disintegrate, and then they formulate. And basically, they use this because they want porous materials, which is like the main focus of why they're using this specific synthesis method. Okay, sample characterization. They're doing X-ray powder diffraction, which is how you get these rings. I took this from our slides in scattering theory, which is like incoming beam into your sample, and then that's how it gets these rings. So the spots lying on one curve is reflections from the plane. And crystals are ordered in a random orientation, and that's what's like important for specifically powder diffraction for XRD. They use this Rietveld refinement procedure. Again, it's just like they're using it to observe determine crystal structures. Yeah, I don't know. They're just like fitting known things to your experimental data. And then they fed in this information, this structural information of space groups, lattice constants, and then this is where they mention card numbers, which is what is used in XRD analysis. And they're fitting uses again this like pseudo void function.
That's the linear combination.
Which one?
A pseudo point function.
Yeah.
It's the same thing used for Brahman peaks.
I remember that for the X-ray diffraction, they kind of rastered through a ton of angles, and then wound up getting the peaks from there to get like all the planes possible from that one specific orientation that the beam was focusing on, or something. Moving that.
Yeah, that's how like XRD. Like that's the process. Is you go through a bunch of angles, and then you're able to see all the the planes that come up at the different angles, and then that's how you get your 2 theta values. All right, and then we're looking at this figure 1, which is TEM micrographs. I saw someone mention that there's no scale bars.
Yeah, I was just about to ask that.
Like literally, what the hell?
Really?
Yeah, but they mention.
Which is the scale?
No, I'm just saying like they mentioned it from TEM. They get 6 to 8 nanometer size pores, which like I guess we have to take their word for it because there's no scale bar.
Also, like, what are you looking at?
Right, like
Right.
what? That looks like a sock. So I don't really know what they're like.
Are the dots what we care about?
I think
The
that
holes, I think.
like bottom left, on the top of that is that bottom left figure is zoomed in. I think.
It's weird. I don't like the bottom half, but
Yeah, it just
I don't
like
know what I'm looking
doesn't make any sense. But they say that basically they're like 6 to 8 nanometer pore size pores, so they were able to create a pore structure from the combustion synthesis.
Yeah.
Then they used SEM to look at the snowflake-like appearance of particles, which were hexagonal morphology, proving that they were able to crystallize things. And then they have an X-ray diffraction pattern, which just confirmed that they made aluminum trioxide, or dialuminum, whatever the hell.
There was something I was a little confused with this XRD. There's a few peaks they have unlabeled.
Yeah.
If you look at it, there's one at like 60s,
Yeah,
and there's like a
this little
bunch
one.
from 80 to
Yeah.
100. I don't know, is that quartz? Maybe, and they just didn't label it?
We're talking about
The XRD graph.
Yeah, like there's a peak here, and then these little peaks here that just like aren't labeled.
Yeah.
Which I'm assuming therefore they're not
Relevant?
relevant to
They are not
aluminum.
yeah.
Sure, but like what is it?
What is that? Yeah.
Because it isn't just noise. Because they
Yeah.
even marked the 1010 peak.
Yeah. That's a good question. I guess if
I guess we could look at it.
I guess we could look up card 88-0826 and you would see in theory, yeah, this. Now I don't know if they were just labeling like relevant planes and they just
Totally.
decided not to, but there's
This is
so
not
many
the best
planes
one.
mentioned already, and not all of them were mentioned in the paper either. So I'm like, that makes me think that they're not. It's not like they just did the relevant part.
I'm sure.
Well, I think maybe the card
It's
stuff.
sapphire?
Well, I don't know about the
It could be like a different fabrication method. So like with the way they did it, there could be residuals from like the combustion materials, possibly.
Well, the residuals from that, they make nitrogen, metal, nitrate, precursors. That's the only other thing that's gonna come out of the combustion.
what peak specifically are we looking at?
60.
At 60, and then like 80 to 92.
I mean, this kind of, yeah.
It looks like the sapphire
This
stuff.
okay.
Oh, it's sapphire.
I can't see it. That's around 60. Looks the same.
Yeah.
Yeah,
Okay.
which they
I
mention.
don't know about higher. It doesn't have any intensity. Oh,
There's someone here.
Oh, it's totally sapphire.
Okay.
So there's the small
It's
face
the-
here.
Yeah.
There's
Okay,
one right at
okay.
60.
The
and then
sapphire
one,
that
two, three,
the
four,
material's
five.
sitting on isn't the like.
Yeah, that's the
Oh, I
AL2.
see.
Okay.
And that is a
Sapphire.
question they could totally ask. Would
Yeah.
that be a mean one to ask?
Yeah,
That would
like-
be especially
This is
because.
Natalie paper, are you sure?
No,
I
this
think it's
can
Garmstein.
not be
I-
Natalie's paper. Natalie works with polymers.
Yeah, you say Natalie's?
No.
Natalie's gonna ask that?
I didn't
No, she
No.
said it
Ah.
would be a possible.
Ah,
I said
okay.
it could be a question.
I don't know.
Yeah, which makes sense because I think sapphire is a very commonly
use it.
used
Yeah.
thing in this, and it would definitely be like, yeah, I
For
can
sure.
see
That's
that.
on
What could be
sapphire?
it possible?
Like-
The little-
Yeah, that's an.
That's the
that's
AL2
a-
thing.
Yeah,
Is sapphire.
That is sapphire?
So from 80 to 100.
but this
I don't know
nickel,
what sapphire is.
nickel filtered copper K alpha. The K alpha is the sapphire part, no? Or not the.
Alpha is the.
It's
uh,
it's the
extra-
yeah the source.
generates
Yeah.
Yeah, but isn't that?
You're not
No.
missing anything from that.
No, the source has nothing. You
That's
can't.
just kind of
that
how intense is your thing.
Yeah, that causes the X-rays.
What energy is your team?
Yeah, but I thought it was related to the.
Maybe it could pick up on
Sapphire
different
itself?
things. I don't think it relates to the. Like you can fit certain.
It is AL2.
Oh, that reminds me. When I took this,
I didn't know that.
there's a polymer characterization course, and they were like, "What is a good beam source for this material?" Right? I think that might possibly be a question as far as like XRD stuff.
I feel like it's a bit obscure. I feel like I've heard that in trainings. For like X-ray stuff.
But yeah, okay, so that's a
Sounds really
good.
complex.
That's a good call out that is the sapphire or like the alpha part of
The
AL2,
non-alpha
It's
part of
alpha.
it.
which they don't mention. They
Talking about alpha. Alpha's just the code.
Right, so it's just like regular sapphire, not
I think
fancy
so.
alpha sapphire. Because alpha sapphire is like special.
I don't know. That might just be sapphire. I don't know.
Is it?
They use
That's
alpha
actually a great question.
AL203. So that's
Right, what's the difference between alpha and regular AL203? That's my question.
it's just a different. It might just be things. That's
Right.
sapphire. I have no idea.
If they didn't,
I don't really care because we know what XRD for alpha is. So and that's
that was alpha?
Yeah.
Oh!
Yeah.
Never mind. Okay,
It's just
same
a
thing.
phase.
Okay. I thought that was a different phase.
Once again, not 100% sure of sapphire, but it's the same chemical structure as sapphire.
And it's
or
an
chemical
alpha.
makeup, sorry. And I'm not sure if sapphire is alpha. phase.
Okay, so you
Okay,
don't know
that's
if that's alpha.
It might be some like I don't know how they got their pores or if they do something different to it for this solution combustion, whatever. Doesn't really matter. I looked up what alpha AL203 XRD peaks and it has those.
yeah.
Okay.
Okay.
So
And there's no mention of sapphire in the paper.
yeah,
So,
they just call it
but like sapphire is a commonly used like
substrate.
substrate for
That's
XRD
nice
stuff.
and slick.
So
So that's from the substrate, and the substrate's also made from AL203.
Well,
The
there's no
substrate is
substrate.
AL2.
There's no substrate.
Okay. What's their process? Why would there be AL203?
Because that's the pores. That's what
Okay.
the.
That's a
Yeah.
scaffolding
So it might
material.
just be, some sort of powdered version.
It's powdered sapphire. That's what I'm gonna say.
Sure.
Yep.
Call it that. Yeah.
Nanopore sapphire.
If you don't want to say AL203.
oh, so they're
that's fine.
mixing sapphire with the AL203.
No, I
That's
think
what
AL
sapphire is.
AL203 is
It's
sap.
the luminous
Okay, we're using
Sapphire.
two words for the
That's
same
why-
thing, and
that's
it's
why-
messing with me, man.
AL203 is
Sapphire.
Sapphire.
Sapphire, yeah.
It's
Jesus
just
Or
Christ.
alumina, whatever you want to call it.
Oh,
I didn't know that, though. That's cool.
okay, so my
See,
lack
I
of
didn't know that
chemistry
either.
knowledge is showing. Okay, cool.
Well, people
So I'm
just say
saying, I don't know,
sapphire.
sapphire is the alpha one.
I fully, like, gun to my head would have said those were two different things. So
So
That's,
those are the peaks you get from the powder. Okay.
yes, and so they're using this as a
Yeah.
template for growing
Nobody
zirconia
knows
because
that.
they want to be able to
I wouldn't
control the size of zirconia crystallites.
And so that's leftover powder, not.
No. It's
No,
just
no,
the
no.
thing. It's just the thing.
Alpha
They just
say-
AL203 is sapphire.
No, I get that. Yeah. Okay.
They just
So
label
they
it.
fired the shit.
Two
Okay.
copies.
They fired the shit.
It blew up.
And
up.
they blew it up.
Yeah.
Okay.
Mhm, mhm.
And we're getting diffraction peaks in that little like 80 to 90 region
Yeah.
that are kind of characteristic of AL203 powder, is what you're saying?
Yeah.
Which is
this thing.
Why?
which
why
means
is
there's
that
leftover
label it.
which
Yeah.
means there's leftover powder from the firing process.
No, they just didn't label those peaks.
But like, why is there AL203 in there?
Because that is all
This whole thing is
AL203.
AL203.
Wait
this
a second.
Is just the
They just didn't-
fraction of as prepared alpha AL203.
Now, do we think these peaks are alpha AL203 and these other peaks are just another phase of that sapphire?
It's literally the exact same.
Yeah.
Like, from
Okay.
their paper.
It should be the same.
So
Yeah,
that's
like a
not
copy
that's
and
not
paste
in the
of the
dusty
same
phase. That's like in the
This
bulk
is
phase.
dusty phase. This is
This is powder.
AL203
Oh, this is
powder.
powder.
Yeah, this is all powder to fresh.
Okay, that kind of
This
messes
as
me
prepared,
because
so
like
this is them
the as
investing and adding the zirconia.
Okay.
So
This
they've
is
blown it
just
up.
The Lumina junk.
Yes.
Mm.
After
Yeah.
they've blown it up.
They just didn't label the peaks for whatever
After
reason.
they made the pores.
Okay.
wait a second. I thought that this paper had the way they make the zirconia aluminum conglomerate thing is by mixing it all up at the same time and then firing it. And blowing it up.
Micron-sized blah 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 was prepared by the combustion of aluminum nitrate blah 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 and
Oh,
urea. So they
okay.
make that and
So
then
it's like a template and then like stuff.
And then they
yes.
Okay.
Because they're
And then
trying
they
to,
nail it.
yeah, because they're trying to
They
characterize the
repeat
template, which like here in results and discussion, which I think is what I'm on now. Yeah, characterization. They're just looking at the template. They're basically trying to confirm if they've grown sapphire and if they grew it at a pore size
Yeah, it's
Yeah.
the pores thing.
good enough to
Yeah.
grow zirconia.
But the
Yeah.
XRD wouldn't tell us that. They're just confirming that they made sapphire.
Yes.
It still is sapphire.
Yes.
Okay.
And
Yes,
then
it
the
still is.
We haven't done
TEM
anything to it yet.
and the
Yeah.
TEM is supposed to show that they have good enough pores,
For sure. Whatever. We can't.
which like, yeah,
If you
useless,
say
but
so.
whatever.
okay.
Then they go into what is it? Preliminary analysis, X-ray diffraction line profile fitting. They looked at 012 and 113 because they wanted the least degree of overlapping, which was they said that a large issue that they had was that a lot of these peaks had a lot of overlapping, and so it was really hard for them to obviously like fit good functions in overlapping data. They did this like profile fitting method, which was the like what's it called? Retville, Reedville,
Oh,
Reedville,
yeah,
what it's
yeah.
called? Yeah. And total integral breadth. So they have this other equation here, which like why is it incorporated in the paragraph? I don't know. Yeah. So they assumed this profile shape was pseudo-void, and then they have all these values. So like this new, or actually I don't even think that's new. I don't know what N is. Gaussian component, omegas, the full width half max, peak intensity. So that's kind of what I mentioned here, that they're using this like line intensity, peak intensity, full width half maximum.
Full width half max. That's like with the peak width and then the middle half max.
You go to half the maximum.
Yeah.
And it's the width, the full width, half maximum.
Yeah.
Okay.
Yeah.
I get that, and I know that there's like a couple of things that relate. There's some papers that we went over that relate like the width of the XRD peaks to like strain and like.
Yeah, which is what we're getting into now. Which
Okay,
is this
awesome.
William.
Oh yeah.
Williamson, I call him William on accident. Williamson Hall
Williamson.
plots. It determines size and strain within a powder. So the pure size broadening is the William Halson plot. Okay, this is unrelated to the current plot. This is in general.
Yeah.
The Williamson. I keep calling him William Halson plot is constant with increase in diffraction vector d. That would be pure size broadening. And if the William Halson plot increases linearly with an increase in d, that's pure strain broadening. But they didn't see that. So they decided that B theta,
'cause they got
which is
both.
their like integral breadth, was increasing non-linearly with diffraction vector.
Just because they're talking about them both happening at the same time.
Yeah, and so this is like their as prepare and annealed templates, and then like the Zirconia alumina template.
Right.
So then the slope of the William Halson plot is strain, and then I remember this being on the quiz for the class. And then the y-intercept, I think, is like crystallite size.
Yep.
Yeah.
Yep. I remember
Yeah.
that.
Look at that. Oh, crap. Go away. Okay, well, I wrote that there. Yeah. Which I truly forgot that we learned that in that class, so that's so great for my attention. Okay, then they go into this, I go into this method more. So this is not experimental, this is computational. So it's parameters that they got from this refinement method. And here they show they mentioned marginal oxygen vacancies. So there are presence of oxygen vacancies here.
This is computational, you said?
Yes, from the refinement method. I mean, they took XRD plots, but then the way that they gathered this data here is from computational stuff.
For revolve refinement, you can tell it what things you want to vary. So you plug in all the rest of the parameters that you already have, and then vary just the oxygen.
Oh, so they're varying oxygen.
And then the program will say, okay, based on I'm varying oxygen and I have this data, this amount of oxygen should fit this data.
Okay.
If the lattice parameters are
Yeah,
X,
yeah.
Y, Z. So usually start with like a computational, just like figure of a crystal cell with all the parameters, and then it'll change it and it'll tell you exactly what it is.
Cheaper one.
Oh.
It's really
Cheaper
cool.
one.
It's really fast too.
Yeah.
Yeah.
It was hard finding information on this refinement method because
It's very powerful.
It's
Yeah.
very niche too.
it was used very differently for different
Mm-hmm.
things, and I didn't know what was standard and what wasn't. So that I didn't include it, but I think in my own notes I told myself to look into this refinement method more. So now they're characterizing the composite, the zirconia grown in the alumina template by 50/50. Also, Italy, what is that? Okay.
What is that?
I think I'm trying to write it, and for some reason.
And it said I will not. Alright.
Okay. There was the presence of only tetragonal phase. This literally didn't show up the other night when I made this. I don't know. Okay, anyway. Presence of only tetragonal phase in the zirconia. Then this is the XRD that they got from it.
That's what we were thinking.
Oh yeah, asymmetry of alumina
That's not what I
reflections in the low angle side.
Everyone thought something different.
So this is the shift thing that I was talking about. That wasn't shift, but was asymmetry.
So from pink to green, or what? Oh.
That's also what they mentioned asymmetry of alumina reflections at low angle side of peaks. And I was like, what? I don't know what the asymmetry
I don't
is
see
because
any shift.
they all look the
They look
same.
like
Yeah, this is definitely me trying to write is or it or whatever. Is sample dependent.
Oh, there's a little smear.
Is there?
Okay. The green one has more tail. Is that what we're looking at?
More what?
Oh.
Like a tail?
Well, it could be a combination.
Am I even looking at the right thing?
Oh, that
Like,
little thing. You mean T? Oh,
There's like more.
like at
But
35.
this is the zirconia. This is zirconia. Zirconia.
But I'm comparing the two.
Yeah. This and that,
Okay.
like right there.
It's got.
That's
Yeah.
a little tail.
Yeah.
I wouldn't say that's a shift though. I would
And then
say
because they
either-
mentioned
I'm just talking about the asymmetry.
asymmetry
Yeah,
of
on the low
alumina
angle
peaks,
side.
but they're looking at the green one. They're
Yeah.
referencing the green one, not the pink one. Because I thought when they said alumina reflections, I was like, oh, they're looking at the template, but they're looking at the composite. And they're saying it's sample dependent, so it looks like it's just a manufacturing thing. All the samples that they made were clearly a little bit different, and so they got this asymmetry. Now I don't know if this XRD plot actually.
How do we see the asymmetry they are talking about?
Yeah, I don't know.
That's what I don't know. They mentioned that there was asymmetry, and then I was looking at it and I was like, I don't really know what they're referring to. They don't call it out in this paper.
Yeah.
They don't circle it or highlight it or have any.
Okay,
And
but
then
from
it's sample dependent. They don't show multiple samples.
Yeah.
Right.
I highlighted this. Observed asymmetry is sample dependent and is not wholly due to instrumental effect.
Right.
Meaning
They're saying it's
we
part
don't
of the. I don't know if
Yeah.
it's from manufacturing or it's a
all
alumina
your papers.
zirconia composite
Yes.
specific
Or
thing.
I also was kind of seeing is like
Great.
I
sample
didn't read
dependent
all of
meaning
them, right?
from batch to batch.
Yeah.
All of these, all
It's
of these other
different.
papers.
But you
didn't
want
read
But then they
them.
don't
Or
show
we can't-
other.
can't say.
Because I was gonna say
Why did
oh,
you
if it's
print
sample
all?
dependent, is this XRD
Because
plot
I
an
will
average?
take
But I
it
don't know. This is
to-
definitely
to-
from one
to
sample.
yourself, right?
Yeah, they're not gonna show an average
And I
XRD.
choose the one that I want to read, and then I will print it again.
So I was
That's
confused
some-
by that, but it didn't. really feel relevant for the rest of the
Right.
understanding of the
I
paper.
think it's just stupid.
But they show significant Gaussian peak shapes of the alumina samples indicate large
Yeah,
crystallite
that
size and prominent strain broadening. I think that was the main takeaway from this XRD plot.
Cool.
Now they do microstructure characterization of zirconia particles and alumina templates. Crystallite size DV, which is volume weighted, in microstrain. Epsilon.
So now they're calculating stuff with the peaks, basically.
Yes.
With the what?
Each peak.
Oh, yeah.
So yeah, so they mention all the
For width of half mass.
yeah. So they're doing these planes, and then they're calculating the crystallite size, and then the strain, and then this part is from the Warren Auerbach analysis. Like, so they applied it just to 111, and they were like, this correlates well with our William Paulson plots. Yeah, crystallite size varies between 200 and 300 angstroms, and the microstrain upper limit varies between 0.15 and 0.6%.
I was a little confused on why the Warren Auerbach crystal size was so different than the one that they saw for the crystal size, like calculated from just the XRD plot.
I was also confused too. I didn't really,
Because that's a big difference.
yeah, because this is like not even in the range of what they mentioned here, but it is technically like their effective crystallite size, so it's the area average, and so I didn't understand why they didn't correlate, but it did correlate, or like they said that it matched their average crystallite size from, I think this is supposed to be
It's
WH.
in
Oh no,
Warren.
Warren Auerbach and integral breadth are in good agreement. So I think from the integral breadth that they did,
Yeah, it's here and there. It's this one. Oh wait, the D effective is different than the DV. Right?
yes,
Okay. So we can't. so
one
now
is volume weighted and one is like area averaged.
Oh.
So that's why I didn't
Wait, but this is they're both
try and
different.
relate them.
These are both on length. But how is this one's also in angstroms? What's the difference?
Yeah, why Samsung's is it is length, right?
Yep.
Why is volume? I mean, what is volume if it is length?
It's still crystallite size.
Yeah, but like, what's the difference between this?
Which one is volume related? DB
Probably.
and the effective.
DV is volume average, volume weighted.
Yeah.
I get that.
What does mean volume weighted?
The crystallite size. Volume weight. Oh, weighted volume.
What does
Probably.
mean? What does mean that? Because if it is volume, what is a length and what is volume? What is volume?
I'm
weighted?
assuming it's like in relation to the rest of the material. Versus the other one is like area average, which I'm assuming is like not involving volume, but involving surface area.
Maybe. Surface area? No, because it's a length. What do you mean?
I don't know. Like I think they're just like different forms of saying the same thing, of quantifying crystallite size.
But it's, they get very different values.
Yeah. Because then they're like, oh, average crystallite size from Warren Auerbach and integral breadth are in good agreement. And then I was like trying to look
Oh, is
for the
one
other one.
from Warren from the integral and one is from
Yeah.
the other one?
Yeah.
Oh, which one is from which?
Let's see.
Remember the shear.
Okay, using a single line integral breadth technique as described earlier, the DV is from integral breadth, which is volume weighted. And then D effective is from Warren Auerbach.
So they don't agree. Well, the
Because then it says here, okay, the crystallite size varies between 200 and 300 angstrom. Okay, whatever. The significant Gaussian shapes of alumina samples indicate large crystallite size and prominent strain broadening. So table 2, which is that one that I have there, shows results of Warren Auerbach analysis as applied to separate the size and strain contributions. That's what they're trying to, because I think they also mentioned earlier that broadening from a peak can either be from size or strain, and they want to be able to like tell the difference between the two.
Right.
The average crystallite size obtained from both Warren Auerbach and integral breadth analysis is in good agreement. I don't think that means they're in good agreement with each other. I think that just means they're in good agreement with
itself.
Oh,
or
yeah.
like with theory, or like with known.
So the ones on the left, the DV,
Yeah.
that's from the sample calculated through the XRD physical stuff, right?
Yes.
Experimental. Then the ones on the right, the D effective, that's calculated through WA, and the DV is calculated through integral.
Yeah.
Okay, and that's computation completely. So yeah, they are a good agreement.
Yeah.
I guess.
Yeah.
Whatever.
So okay.
Wait, so what's the difference between, just a second, what's the difference between the DV on the far right and the DV here?
The one on the right was the calculated thing. The ones on the left were from
The
Yeah.
XRD.
XRD
Okay.
plot.
Okay.
Which so I guess they mean like this is in good agreement with this, which
It's fine.
which
So I
like
wouldn't,
sure.
like, they're like one number.
Yeah. But they only
Sure.
did the analysis on like one
Yeah.
Yeah.
one plane, so
They say
or
so.
one direction or whatever.
I mean,
So
it's the same order of magnitude.
231 versus 307.
I mean, as far as computation matching your experiment.
That's pretty good.
yeah. So I think they were trying to then just say that kind of late in the paper to do it, but like that this WA method is like a good means of describing experimental stuff because they were using this for other stuff as well. Yeah, and then we're on to table 3, which is on that same page. The incorporation of zirconia particles in the alumina matrix results in localized deformation due to, I think they mentioned it, but the difference in thermal expansion coefficients, and also just like variation
It's the answer for
and
everything.
stuff. Yeah, pretty much. And the origin of strain is in the interfacial region, so they're like the pore inside the holes. So higher levels of microstrain in the matrix due to the William Hall supply, which made sense. Which if we go back to this, we have way higher values here for this like composite, and it's also linear, which agrees with like what the plot should be telling us for size and strain broadening.
Is beta strain on that Williams?
No,
So, because you said it was higher, I know the slope is higher, which is
The
strain.
y-intercept.
Yeah.
That's
So
the grain
so
size.
yes, I guess technically this beta star. I don't want to say that beta star is strain, but the y-intercept itself, which I guess is beta star.
Well, the y-intercept is crystalline size. The slope is strain.
Yeah.
Okay.
Yes. Slope of the plot is strained. Y-intercept is crystalline size. Yeah. So a decrease in crystallite size and increase in microstrain. There's zirconia crystallites incorporated inside the alumina pores leads to more defects. Which. Yeah. Then they mentioned they have this. Decrease in crystallite size leads to increase in lattice strain. I could have told them that. Like duh. Okay. Then they use the same refinement method for the alumina zirconia samples performed using isotropic strain broadening. This is just like more analysis they're doing. More fitted, they're fitting and fitting and fitting. So comparing to table 1, they had higher values of lattice microstrain and lower values of crystallite size. So the zirconia template, or the zirconia particles grown inside the pores of the alumina template, the difference in thermal coefficients induces residual stress. And also, what makes me think it's Garmestani because we also did residual stress and strain talking about it, and I remember like looking through it because that's where we got the Williams and Hall plots was from strain. And then in the notes he mentioned residual stress, which is probably why I left that one slide in the back blank because I wanted to include that information. But
Side note, do you remember in class how he said everyone messes up the stress and strain plot? And then he said words. And I don't remember what he said, and it was something about the broadening versus the shift.
yeah.
Do you remember what I'm talking about?
I definitely have also a note in my notes, which now I have to go through that. I went through so many notes. I have somewhere where he mentioned, oh, this could be on quals. And I remember like starring it because that literally just came to me now. And I remember starring it because I was like, oh, that's going to be relevant in my life like in a year or something.
Yeah.
So I'll have to go back.
Good job, past you. That's great.
I know. I was like shocked. But yeah, so I guess let me update. There's like I think this is the end. Oh yeah, conclusions, okay. I'll update the slide with more residual stress stuff because now that I'm like looking at it, I'm realizing I probably should have included more. And then I'll try and find that note. The thing is, like, it's literally probably 5 words on like hundreds of pages of notes that I have. So yeah, basically, thermal expansion coefficients of zirconia and alumina are different. They create stress.
No shit.
Crazy. And high values of microstrain. Yeah. Because then also in our stuff we talked about like microstrain, microstress.
Oh my gosh.
Stuff like that.
Did
So
they ever talk about in this paper how that strain affects the actual crystal structure at all?
no.
Oh, okay.
Well, they did
I
talk
mean-
about the shift, the Marial. What was it? The. Starts with an M.
Oh,
Just like-
martinistic.
Martinistic.
Yeah.
Martinsitic.
Martinsitic.
Martinistic.
Yeah.
Martinsitic.
Martinsitic, yeah. Martin sites basically.
Here. Martensitic phase transition. They're only looking at tetragonal and cubic
Oh, this thing.
material, like
Oh, yeah,
phases
great point.
in
Not even
these.
looking at that.
They talk about how there's this shift, Martensitic shift from tetragonal to monoclinic. That happens at this phase transition temperature, and they want to lower the transition temperature by doping, which
Okay.
helps facilitate the stabilization of the tetragonal phase.
Oh, but that
But
was
through
at
the-
the very beginning, the
Yes,
intro. Yeah.
But through the rest of this paper, they only look at tetragonal and cubic, so basically pure zirconia.
Okay.
They don't dope. But they said it all in the beginning.
Right, that's the thing too, is like they mentioned doping, so I was like, oh, they're gonna dope it.
I know, but
And
they,
they
didn't.
And then, okay, so in my conclusions,
And there was nothing about oxygen vacancies, like at all.
no, because they mentioned the bottom thing, oxygen deficiency seen. Size stabilized zirconia is an oxygen deficient form, which is like one of the last sentences they include.
Yes, I see it.
But they say structure refinement reveals they literally say large amount of oxygen deficiency, but then when they refer to the chart in the paper, they mention, they literally say like marginal oxygen deficiency.
And this, is that for the table 4? Because I mean, I'm assuming that's what they're talking about, comparing table 4 to. Where's
Table 1 was the
table
original.
1? This one? But this is as prepared, this is just the alumina.
Yeah, but the oxygen site site occupancy is like very similar.
But this is with just the alumina, table 1, and table 2 is with alumina and
Yeah,
zirconia. So
in
how
the-
did you make
This oxygen and oxygen site values don't really change. There's no significant difference between the two.
Which they don't.
Which I was just confused because when they referenced the oxygen vacancy at first, they said marginal vacancy, and then at the end they're like large amount of oxygen deficiency.
Well, okay, they could be saying in comparison to the alumina, the zirconia has less oxygen. It's 0.9 versus 0.8. I don't know what oxygen.
Because one's like, oh yeah, alumina zirconia 0.8, 0.9. I don't know. I didn't, that like, the fact that they just like didn't answer the question that they said that they were going to answer, and they kind of did, but like, I don't know, I didn't think it was a very like robust answer to the question. They kind of like said the question and then at the very end answered their question, but then they like included all this other bullshit that I was like, yeah, it's like, okay, I'm gonna like learn
It
it.
was a badly written paper.
Yeah, I just like didn't love it.
I agree.
Are they looking at the percentage? Percentage is different.
Yeah, the percentage is pretty different, and this is
But like also their
oxygen
errors
sites.
are kind of bad. Like
that
a
error?
0.8, yes, because the tables are reported values and their errors.
Oh, that's
0.3 with 15% error? Or 15 plus or minus?
What?
Which
Wait, what?
I'm like,
No way.
also what got me is like the way that they're reporting the values in this table is like a fifth grader reporting values in a table for the first time.
Yeah.
Because I'm like, they include these errors, and I'm like, are they saying there's a point
and
85% site or oxygen site occupancy in zirconia with a what 28% error? Is that what that means?
There's no way. This makes
So-
no sense.
The error is specifically like the way that they reported the error along with the value just like really didn't make any sense because I was like, there's no.
Maybe it's in the.
It's not even clear that that's the error on the
Yeah.
table.
Yeah, and the only way that I knew that was because they say like we were like whoever the first chart I think is mentioned.
Fire was carried out. Figure 5 shows.
Yeah,
Yeah, table 1.
Surface level. It's like, oh, that's being great.
Table 1 lists the fitting parameters and their errors.
Yeah. That's all they mentioned.
Is that
What?
the error? Is 0.9,
Yeah, I think
0.8 the error?
Error as in like percent error or like percent what?
That's what I was like, I don't know, like, okay, I'm assuming the thing in the parentheses is an error,
Table
but
one or
also
table or table 4.
all of them.
Okay.
Every table,
They all look the same.
and also not
Yeah.
all values
So-
have an
No,
error.
that's right.
Yeah, why do some?
It's true. I don't know what this is.
Because, like, okay, like for this table 1, for the crystallite size, 120 with the 2 with what?
2 keep
120 angst or nanometers with a 2 nanometer error. I guess that makes sense. Like,
That makes
Yeah,
sense.
That's fine.
That's fine, yeah.
but what is this like? Oxygen and oxygen site occupancy,
sense.
which is like the orders of magnitude between the error and the value
Yeah,
are just
maybe
like
it's percentage. Yeah.
they were
It's
too.
like
Yeah.
0.1 and 0.6. I was like, no, never mind.
So that was another point I didn't make, but I think I like in my head I was like, I just think the tables,
I've never seen that.
yeah, were just like not very well.
Undergrad did it or something.
I know
Yeah.
they weren't very well reported because it just like didn't help to understand specifically like the simulation information.
This is someone's screen here, so
He was also
check this one.
from like, oh wait, yeah, I was gonna say I thought it was
How
old.
recent?
It's not bad.
Okay, errors. Other errors. I have similar errors. Sorry, that was not a sentence, but other refinements look pretty similar.
Really?
So they
That is a
showed
plus
thing
or
in this
minus
case.
number?
No, that's like a big number in parentheses. I don't know what it means yet.
Oh.
Or maybe it means that
They
means
just write
something.
it that way.
Yeah. They
Yeah.
write it
No,
that way,
that's
like-
fine if that's like a specific, if that's specific to the
It's just how they do
red
it.
filed whatever refinement, but like they should at least include
Yeah.
something.
Did they include it?
You should look closely at the values of the parameters and the errors. The smaller these are, the more precise the corresponding parameters have been determined. I think just lower, it's more precise, but
So
when the
it's
red,
like
oh,
R
hold on,
squared
hold on.
thing?
When the Renfield parameter is equal to or less than approximately 3 times the error, thing in parentheses, and the parameter value is not more significant than its error and must be treated with caution.
Let's
So,
say it again. Okay.
for example, if we're looking at table 1,
Yeah.
the error for unit cell A, the
0.1.
thing in the parentheses is not 3 times,
Not
or-
12.
it's not 12.
Okay.
So which makes
Therefore,
the unit cell.
It's fine.
So you want it to be below whatever the 3 times the thing is.
Yes.
But for like the oxygen and oxygen site occupancy,
way higher.
is
Way.
Yeah, it's
way-
more than 3 times for
So-
sure. It's
I
So
mean
this
it's
is
like
how well it fit. Here.
okay, which like I guess makes sense because I assumed like a higher. That's the only other thing I was like, yeah, I guess a higher number in the. I mean, yeah, a higher number in the air is bad, but I didn't know like, you know how.
okay.
So we cannot trust this.
Which
We
now
cannot
like
trust
Cool.
the oxygen
whole-
side occupancy.
like the whole point of this was like is whatever their
Especially the
Question
whole
was-
oxygen site.
You think
Occupancy, it's terrible.
Yeah.
I mean, some of them are okay. Like,
yeah, this opens up a relevant question whether size stabilized tetragonal zirconia or even cubic zirconia is actually an oxygen deficient one, and a detailed structural analysis of zirconia
If the error is too high,
nanoparticles
why they
may
make
solve
this
the
in the first
controversy.
place? Right.
So therefore the like stuff that's supposed to be relevant is this oxygen stuff,
And they don't know.
and it's like not even like
Well,
statistically significant.
I would
So-
argue they care more about strain, and the strain values were good.
Right, which
They
then
just leave
also
it
leads like just like
Then just
then
leave out the other
the
stuff.
whole like structure, like how the paper's written, was just so confusing because it's like we're answering this question, but then they talk about all this other stuff and then like very quickly answer their question at the end with
probably-
stuff that isn't significant. So
Probably some
We
undergrad.
didn't have enough to put make another paper, so let's just switch it in this one. So it's irrelevant with the same data.
yeah,
Or an undergrad project.
so yeah, so this is why. Not this is why. This I think this paper's from Dr. Garmestani. He's an XRD dude, old guy.
Also angry at this year's students, so he might make it
Really?
hard.
Really?
Remember the message he sent out?
Why is he angry?
He wasn't angry. I don't
Disappointed.
think. He was disappointed.
Why?
For what?
Because the
Why you
scattered
did it?
class
Just it's
is
your fault.
He was upset at himself for teaching it bad. is what
also
I
the
got out of it.
students.
But he's definitely gonna take it out on us.
What did the students do? I don't
There
get
was
it.
like a
Yeah,
lot
what
of
did
stuff
you
in
do?
No
class.
one showed up. In
What?
conclusion, no one
Yeah.
showed up to the
No
class.
one
What? Oh, you
We
guys
were
are
like-
finished.
we
It's
showed up.
over.
I would say
us
us
three.
three showed up pretty much
time.
every day. I mainly because I'm like, what else am I gonna do at 8 in the morning? But
What, was it an online class? Or?
Well, no, but all the videos were all online.
Okay, he put the videos online.
So
There was a Zoom portion. I think the only times I
Okay.
joined on Zoom when I was like literally out of the state.
So most people just didn't go to the
no,
class
but then
in
people
person.
wouldn't do Zoom either.
Oh.
Oh no, that's bad.
Yeah.
Because we had a quiz every Friday.
Yeah.
Like,
And they still didn't show up?
no, they took the quiz, but some people would also take it online. Or like if you joined online, he wanted you to turn on your cameras, but then people wouldn't turn on their
It was a
cameras.
weird
But then he
class.
just like wasn't very
He, like-
consistent
But
on
he
what
was
happened.
very
Donuts.
disappointed.
Yeah.
So I think he's gonna make this a little more hard.
Yeah, because then he also, when we did XRD, lab on XRD, he wanted us to do multi-phase, and then
He's trying
They
to
couldn't
coordinate it
get
with
together.
them.
yeah, and then the guy
They
base.
Well,
couldn't
David was
communicate.
busy.
David
Like,
was busy.
Yeah.
Ramstein wanted stuff to happen. It
Yeah.
didn't happen. So we only ever did like 1, 2 labs.
Yeah.
Labs.
One
Yeah.
was like completely like we didn't even go into the lab, and then the other lab was just single phase,
Yeah.
even though it was supposed to be multi-phase,
which thank God it was.
which was helpful
Yeah.
because I like learned. It was like, you know, now I feel like I vaguely know how to like, you know, read XRD graphs and whatnot, but like I don't know.
But yeah.
I was reading
Basically,
multi-phase.
yeah, sent out a message at the end of the semester like, hey, I'm sorry I didn't teach this in like a good order. Like I tried something different this year. It didn't work out. And
No, it was way sadder than that.
yeah, it was very sad. I wonder if I can find it.
It was the saddest message I think I've ever
It's
Yeah.
very depressing.
I tried
And he was
going
going through stuff like the whole semester.
Someone
Yeah.
died. He was
Somebody
at a
died.
funeral
He was,
in one of
like
the
in a
classes.
Zoom funeral.
A Zoom
And
funeral?
Yeah.
was like listening to it while he was teaching and everything.
Of one of his
Wait,
friends.
It
really?
was like, yes.
Her daughter died of like, well, no, yeah, the daughter died of like cancer, and the mom. committed
Wait a
suicide.
second, I'm
Anyway.
recording all of this
And he's
stuff.
Oh,
I gotta cut that out.
Sorry.
I gotta cut
Nobody knows who this person is. I don't know who this person is.
Yeah.
that.
Have you stopped?
No, I haven't stopped. I haven't stopped. Okay, but we're done, right? Okay, yeah.